our text modeling and analysis methods for early detection of leakage points in gas transmission systems. Here our agenda. We will talk importance and safety of gas transmission system, mathematical modeling, practical application of non-stationary flow, dynamic flow leakage detection methods, and our future perspectives for the world. Today, the issue of determining leak points based on the analysis of unsteady gas flow parameters in gas pipelines is one of the most critical problems in the detection of gas leaks. The relevance of this problem stems from several factors. One of the reasons is the preservation of resource for future generations, preventing gas supply interruptions for consumers, reducing economic losses, and at the same time addressing one of the most significant global challenges today, the prevention of environmental pollution contamination. This is particularly hazardous for underground trunk pipelines, as the operation can continue without visible cracks. Later, these cracks grow, ultimately leading to a catastrophic failure of gas pipeline. To ensure the efficient and safe operation of complex gas pipelines, addressing the detection and elimination of gas leaks is critical for timely identification, reduction, and minimization of natural gas loss. This has been a subject of numerous studies by scientists worldwide due to its importance. Given Azerbaijan's rich underground natural resource, Azerbaijani scientists have conducted several studies and, as a result, developed methods for modeling and analysis to initially identify leak points in gas transmission systems. Therefore, gas leak detection systems deployed under various working conditions must meet high standards, including high efficiency and operability, sensitivity, accuracy, automated real-time detection, resilience to interference, environmental safety, and sustainability. Causes the use of mathematical expressions that allow for the precise calculation of gas losses during accidents is one of the crucial tasks for ensuring the continuous operation of these systems. The prevention of accidents primarily relies on adhering to industrial safety requirements and the operational rules gas distribution networks. It is critical to strictly monitor the integrity of pipelines and ensure there are no cracks in the gas pipeline systems to avoid compromising its ecological and economic aspects. Methods used to detect pipe leaks are divided into two categories: software and hardware systems. Software systems typically detect leaks and determine their location by collecting data from pressure, temperature, and flow sensors. Hardware systems, on the other hand, use sensors that are not used in regular pipeline operations. There are four main approaches to solving leak detection. Pressure wave methods. This method is based on detecting the pressure wave generated during a gas leak. To determine the lower limit of the leak, changes are recorded on a 100-kilometer pipeline with an approximate error of 500–1000 meters over 5–10 minutes. However, this method requires continuous monitoring. Hydraulic correlation method. This method, we can see that restores piezometric levels based on the pressure indicators in the pipeline and allows leak detection with an error of 1,500–2,000 meters on a 100-kilometer pipeline. Sensor performance is crucial, but in some cases false signals may arise. And third, our acoustic method. This method detects gas leaks by identifying high-frequency sounds. It provides a detection accuracy of 1.5 meters, but is costly, requiring sensors to be placed every 100-300 meters. And fourth, differential flow balance method, using flow measurement devices, allows detection of small leaks in pipeline section and is the most accurate method. A number of equations have been obtained based on the numerical solution of the mathematical model of pressure changes, which allows for the detection of small leaks in unsteady flow. The main distinction of our study is the development of a computational scheme that enables the detection of gas leaks in a short time frame. On the other hand, only 2 pressure sensors will be installed at each pipe section, which reduces the cost of systems. The sensors placed at the beginning and end of the pipeline will be acquired at the control point, which enhances the effectiveness of the control point. When solving this problem, it is advisable to study unsteady process and obtain mathematical expressions that will control the emerging physical processes. For this, unsteady models need to be used. The requirements of mathematical models force us to maintain a balance between BUs, compatibility, and simplicity, which requires us to closely monitor the physical processes of gas flow through the pipeline. When selecting between these methods, factors such as pipeline length, diameter, environmental conditions, and economic efficiency must be considered. Modern studies show that mathematical modeling and analytic methods provide the most accurate and reliable leak detection. In our research, mathematical modeling is used to develop a system of equations that allows for the detection of small leaks in unsteady flow conditions in a short time frame. And you can see in this photo, first pipeline of the gas pipeline and second initial pressure of the gas pipeline. And wireless pressure sensors are designed to monitor pressure fluctuation at the beginning, x equal 0, and the x equal L of the gas pipeline. As shown in this figure, it is proposed to install these pressure sensors on the pipeline at the starting and ending sections. These sensors allow the monitoring of pressure variations in the pipeline through the internet and the control station. It is clear that solving the non-linear system of equation is not possible because such equation cannot be integrated. Approximate methods are used in engineering calculations, meaning that the equations are linearized. The following linearization methods are used to solve the equations. During the calculation, it was shown the Chernov's linearization is more favorable when the pipelines are damaged. The expression characterizing this linearization as follows. Here, 2a represents Chernoff linearization factor. Thus, to further determine the given process, the solution of equations should be sufficient, provided that initial and boundary conditions are correctly specified. In the initial condition, the distribution of the source function pressure along the legs of the pipe at time equal 0 is given, assuming that inertia forces are not considered. The boundary conditions are specified to ensure the prescribed law-abiding change in pressure and flow at the endpoints of each segment of the pipe. Properly specifying the boundary conditions completes the mathematical model of the process and allows for comprehensive and accurate investigation of the physical events occurring. Thus, based on the investigated physical process and in this figure, we accept the expression representing the initial and boundary conditions as follows. Initial and boundary conditions, time equals 0 and px0 equal boundary conditions for the main sections of the pipeline as follows. And we can get this formula. And in experiments, when the integrity of the gas pipeline is preserved, the Laplace transform method is preferred. The Laplace transform converts the equation into second-order ordinary differential equations and describes the transformed propagation of pressure along the pipeline under the given conditions. To obtain the original solution of the equation, we use the inverse Laplace transform rule. Thus, when the initial and boundary conditions are given, the mathematical expression representing the propagation of pressure along the length of the pipeline over time is obtained as follows. This equation describes the transformed propagation of pressure along the pipeline under the given condition. Using the above equation to determine the pressure variation law of the gas along the pipeline for different gas leaks points. Initially, by assuming the leakage point L second equal 1.5 for 10 power 4 m in the pipeline, we calculate the pressure values of the gas every 100 seconds and every 12.5 kilometers, including the leakage point and the 95th kilometer, and record them in the second table. The advantage, I will show you table. The advantage of unsteady gas flow models is that they allow for the analytical determination of the leak location using pressure variation values over the time. The difficulties, however, arise from the impossibility of completely eliminating relative errors in determining the exact location of breakage or cracking. On the other hand, the advantage of steady-state gas flow models lies in the simplicity of calculations and accurate identification of damaged area. However, their drawbacks is that after a pressure drop occurs at certain points along the pipeline, a certain amount of time is required for a new steady-state flow conditions to establish. During this time, a portion of the gas is released into the environment. The occurrence of a gas leak in the pipeline leads to the formation of unsteady gas flow. The duration of the unsteady regime depends on the time required to transition from one steady state to another, is related to the propagation speed to the pressure waves along the pipeline. The pressure wave in the gas flow propagates at the speed of sound. Therefore, when the pipeline length is 100 kilometers, the duration of the wave's movement will be approximately 5 minutes. Thus, it is not difficult to direct and to detect a leak by observing the pressure drop along the pipeline. Let's examine the pressure drop ratio at the beginning and end points of the gas pipeline. If the leakage occurs at different parts of the pipeline, the pressure drop ratio varies. If leakage occurs at the beginning, the pressure drop ratio is 190 times higher than the one at the end. If leakage occurs in the middle, the pressure drop ratios are approximately equal. If leakage occurs at the end of this pipeline, the pressure drop ratio at the beginning is much smaller, 0.002 times. During the fixation time at the constant time interval, time equal time 1, it is possible to observe the deviation of the pressure change from the value in the operating mode. The ability to detect small gas leaks directly depends on the accuracy of the measuring instruments. In an automated dispatcher control system, real-time calculations are performed for any change in the gas pressure. In this case, the real and calculated pressure values for each segment must be quickly compared. Therefore, determining the minimum time to deliver reliable information and to the dispatcher center is an important task. To verify the calculation results, to perform engineering calculations, we accept the known data and parameter obtained from the calculations. By using equations and considering different leakage, we determine the leak location and compare the calculated value with the actual value. The calculation results are recorded in the following table. By using this data, we can validate the calculations and ensure the accuracy of our model. The engineering calculation based on the given parameters allow us to determine the exact location of the gas leak and evaluate the performance of the system under various operating conditions. These results are critical for ensuring the safety and efficiency of the gas pipeline systems and for preventing accidents by detecting leaks as early as possible. The detailed information and data will be presented in the tables and graphs, which provide a comprehensive overview of the results. This table shows that the calculated leakage point is accurately determined only at t equal t1 and equal 300 seconds, and the relative error is minimized. The reason for the relative error is simplification of the nonlinear equation system and the simplification of the mathematical expressions. However, this is accepted for engineering calculations and dispatcher stations. In fact, the principle of the mathematical expressions obtained from the study of physical processes and applications of the new calculation scheme are suitable for practical use. Nevertheless, these principles are fully accepted for engineering calculations and dispatcher stations. The mathematical expressions obtained from the study of physical processes and the application of the new calculation scheme have proven to be suitable for practical use and can be effectively applied in real time. Based on what we have demonstrated above, in conclusion, we reach the result that by using mathematical modeling method relates to unsteady gas flow, a more accurate description of the process occurring in gas pipelines has been achieved. Within this framework, analysis based on gas dynamic equations has been performed studying pressure distribution when the leakage point is located at different positions. New effects have been discovered as the accuracy of exciting computational methods has been improved. As a result of modeling the parameters of complex gas pipelines during emergency situations, a new computational approach has been developed to determine the minimum fixation time for recording unsteady flow parameters. The proposed method enables the development of optimal strategies of the efficient and safe management of gas pipelines. Additionally, a new method has been introduced for the rapid detection of gas leaks and their integration into control system based on the observation of pressure changes at different points along the gas pipeline. This approach helps to more quickly identify emergency situations and ensure environmental safety. The developed analytical method is suitable for engineering calculations and offers practical implementation possibilities. Thank you for everyone for listening.